Hello my dear students, in the last class I explained about Euler's theory, Euler's crippling load and also a different end conditions. So Euler's formula, what it says, crippling load PE is equal to pi square EI divided by LE square, where LE is the equivalent or effective length of the column and E is Young's modulus and I is moment of inertia. Okay, PE is crippling load. Here the equivalent length of the given column with given end condition is the length of an equivalent column of the same material and cross section with both ends hinged and having the value of crippling load equal to that of the given column. That is the meaning of equivalent length. And also you should remember always while solving the problems, the vertical column will have two moment of inertia, XX and IYY. Since the column will tend to buckle in the direction of least moment of inertia, therefore the least value of the two moments of inertia is to be used in the relation. Means you have to consider the least value of the two moments. You have to calculate both IXX and IYY and take the least one to calculate the crippling load. Here P is equal to pi square EI divided by LE square. Here I is the least value you have to calculate. Okay, so this I have shown in the last class with the figure. So I just showing it again. When both the ends are hinged, LE means effective length, that is equal to L. So the formula becomes pi square EI divided by L square. So this is, it remains same, pi square EI divided by LE square. One end fixed and the other end is free. That time LE is equal to 2L. So if you substitute here, the equation becomes pi square EI divided by 4L square. When both the ends are fixed, LE is equal to L divided by 2. So if you substitute in this equation, we will get 4 pi square EI divided by L square. One end fixed and other end hinged, LE is equal to L divided by root 2. So P is equal to, when you substitute in this equation, you get 2 pi square EI divided by L square. You no need to remember all this formula. You just remember P is equal to pi square EI divided by L square. Then directly if you know this end condition, you can substitute that LE value in this equation. Okay, let us take one example. A steel rod 5 meter long and 40 mm diameter is used as a column with one end fixed and the other free. Determine the crippling load by Euler's formula. Take E as 200 GPa. Okay, here steel rod is given of 5 meter length and the diameter is 40 mm. Okay, the modulus of elasticity is 200 GPa, so that is nothing but 200 into 10 raised to 9 Newton per meter square or 200 into 10 raised to 3 Newton per millimeter square. So first thing we have to, we know the formula, right? For a crippling load, PE is equal to pi square EI divided by LE square. So for that we required I. What is I here? It is a steel rod. It is a circular, cylindrical steel rod it is. So I is equal to pi divided by 64 d raised to 4. So substitute d is equal to 40. Substitute in this 40 square, you get 40,000 pi mm square. Now you have to see what is the equivalent length of the column. LE is equal to 2L. Why? Because one end is fixed and the other end is free. So when one end is fixed and other end is free, L effective or LE or effective length, that is equal to 2L. So 2 into L is length is 5 meters. So 5 into 10 raised to 3 millimeters. So simplify, you get 10 into 10 raised to 3 mm. Next, find the Euler's crippling load, that is PE is equal to pi square EI divided by LE square. So pi square into E is 200 into 10 raised to 3 into I is 40,000 pi divided by LE, 10 into 10 raised to 3 square. Okay, simplify this, you get PE is equal to 2480 Newton. Okay, so this way you can calculate the Euler's crippling load. We'll take one more example. Calculate the safe compressive load a hollow cast iron column with one end fixed and other hinged of 150 mm external diameter and 100 mm internal diameter and 10 meter length. Determine the crippling load by Euler's formula. Take E is equal to 95 giganewton per meter square and factor of safety is 5. Okay, so here you have to calculate the safe compressive load. Okay, so safe compressive load is what? It is load PE is equal to pi square EI divided by LE square. So safe compressive load is divided by factor of safety. That gives safe compressive load. Here you have to see what is L effective. One end is fixed and other end is hinged, and capital D is 150 mm because external diameter is 150 and 100 mm internal diameter, that is small d is 100 mm, and E is equal to 95 giganewton per meter square or 95 into 10 raised to 9 Newton per meter square or 95 into 10 raised to 3 Newton per millimeter square. Factor of safety is 5. So let us first find the moment of inertia I. See, this is a hollow cylindrical section. So I is equal to pi divided by 64 into capital D raised to 4 minus small d raised to 4. Simplify, substitute D is 150 mm whole to the power 4 minus small d is 100 mm to the power 4 into pi divided by 64. Okay, now here one column is fixed and other one is hinged, so effective length is equal to L divided by root 2. So using the conditions, so L is equal to L divided by root 2. So L is equal to, what is the length? Length is 10 meter, so 10 into 10 raised to 3 millimeter divided by root 2. So you get 7.07 into 10 raised to 3 millimeter. Then you can use the Euler's crippling load, that is PE is equal to pi square EI divided by LE square. Pi square, E is 95 into 10 raised to 3, I convert into millimeter, into I is this value, substitute the value and write here, divided by LE. L is 7.07 into 10 raised to 3 square. Okay, you get 374 kilonewton. This is Euler's crippling load. We want the safe compressive load. So safe compressive load is equal to PE divided by factor of safety. The factor of safety is 5. So 374 divided by 5, this is equal to 74.8 kilonewton. So in this way you can calculate what is Euler's crippling load and what is the safe load. Okay, we'll take one more example. A hollow alloy tube 4 meter long with external and internal diameters of 40 mm and 25 mm respectively was found to extend 4.8 mm under a tensile load of 60 kilonewton. Find the buckling load for the tube with both ends pinned. Pinned is nothing but hinged. Okay. Also find the safe load on the tube taking a factor of safety as 5. Okay. Here also you have to calculate safe load. So for that first you have to find the crippling load, then divide that by factor of safety, that gives the safe load. Okay. What is given here? Length is given, that is 4 meter long, and external diameter capital D is 40 mm and internal diameter is 25 mm. Okay, and it is found to extend for 0.8 mm is nothing but deflection, that is change in the length, is equal to 4.8 mm. Then tensile load is 60 kilonewton. Okay, that is 60 into 10 raised to 3 Newton, and factor of safety is 5. So what you have to calculate, pi square EI divided by L is, crippling load is equal to pi square EI divided by LE square. So first let us calculate I. You have to calculate area also. Okay, because we have to calculate E here. E is not given. Okay, E you have to calculate Young's modulus. Young's modulus is stress divided by strain. For stress, that is equal to load divided by area. For that that purpose you have to calculate area also. So area is, this is a hollow cylindrical section, so area is pi divided by 4 into capital D square minus small d square. So pi divided by 4 into 40 square minus 25 square is equal to 765.8 mm square. Then moment of inertia, that is pi divided by 64 into capital D raised to 4 minus small d raised to 4. Okay, simplify this, you get this value. Now we have to calculate strain, because we want to calculate Young's modulus. So strain is equal to change in the length divided by original length. Change in the length, that is given 4.8, divided by original length, that is 4 into 10 raised to 3 millimeter. So you get 0.0012. Now you calculate what is stress. You can directly calculate using this formula, or you can first calculate stress and then you can find E is equal to stress divided by strain. Okay, here I have used directly E, Young's modulus, is equal to stress divided by strain. Stress is equal to load divided by area into strain. Load is 16 to 10 raised to 3 into area is 765.8 into strain, that is 0.0012. You get 65 to 90 Newton per millimeter square. Now here in this case the column is pinned at its both the ends, means it is hinged at both the ends. So what is L? Equivalent length of the column LE is equal to L only. First condition, both the ends are fixed. So L is equal to L, that is equal to 4 into 10 raised to 3 mm. Now you substitute in the equation Euler's buckling load, PE is equal to pi square EI divided by LE square. Okay, so pi square into E is now 65 to 90 into I is calculated value 106500 divided by LE is 4 into 10 raised to 3 square. So you get 4290 Newton. Okay, you can write in terms of kilonewton. So divided by 1000, it gives 4.29 kilonewton. We have to calculate the safe load. So safe load is equal to crippling load or buckling load divided by factor of safety, that is equal to 4.29 divided by 5 is equal to 0.858 kilonewton. So like this you can calculate what is Euler's crippling load, Euler's safe load. I hope all of you understood. If you have any difficulties, we can discuss in the class. Thank you.